So can all of you hear me fine?
I can hear you fine.
Okay, perfect. So it is an honor for me to introduce today's speaker, Professor Kallol from Humboldt University, Berlin. I actually knew of Kallol for quite a while before I met him, since I was working on high-valent iron oxochemistry in Chris Cheng's group, and I read about his postdoctoral work with Professor Larry Kay. So Kallol graduated with a Bachelor of Science from the University of Calcutta and a Master of Science from IIT Kanpur. He then completed his PhD studies with highest distinction at the Max Planck Institute for Bioinorganic Chemistry in Mulheim, working with director Professor Karl Wieghardt. Then subsequently, he conducted his postdoctoral research with another pioneer of bioinorganic chemistry, Professor Larry Kay, at the University of Minnesota, which was when I actually started hearing of him, because Larry's daughter was actually my lab mate. So then in 2009, he joined the Humboldt University in Berlin as a junior research group leader within a cluster of excellence unifying concepts in catalysis. So I first met Kallol in person actually in 2014, the second time of which was when Singapore hosted the International Conference in Coordination Chemistry. And then in 2016, he became a Heisenberg Professor of Inorganic Reaction Mechanism and Spectroscopy with his work directed towards transition metal-mediated CH bond activation reactions. So he has received a number of awards, and I'll only name a few. So this includes the Eurobig Medal, which Kallol just mentioned, the Ernst Haag Award, the European Journal of Inorganic Chemistry Young Investigator Award, and the Karl Duisberg Award from the German Chemical Society. So he was gracious enough to host me twice, actually. Once when I visited Humboldt University, and the second time was at a conference in Erkner. So Kallol kindly agreed to join us for this webinar very soon after I contacted him in June. And although I would have preferred hosting him in person, we are really privileged to have him speak to us today. So Kallol, the floor is all yours.
Yeah, thank you very much, Hansen, for the kind introduction. It's really a great pleasure to be able to share some of the work that are going on in my group with you all. I would also rather be in person in Singapore. I love being there. I was even at a point of moving to Singapore at some point. So, okay, let me check. I have too many. Is it fine now?
Yes.
Okay, great. So yeah, right. So, but somehow, yeah. So finally, because of family reason, because my son is really a soccer crazy person, and he would rather stay in Germany, and he is in professional soccer. So that's maybe one of the reasons I decided to still stay. Otherwise, Singapore is really a fascinating country, and I love being there. Anyway, so today I'm going to talk about small molecule activation at transition metal centers. We are doing a lot of spectroscopy, and we are trying to trap reactive intermediates. But today, amongst many small molecules that we deal with, like carbon dioxide, hydrogen, oxygen, in the interest of time, I would mainly deal with oxygen. Now, I call myself a kind of bio-inspired chemist, so the work that we do is to some extent inspired by nature. So nature uses different kinds of active sites for activating dioxygen. So you can think of this very typical porphyrin a heme center. It's a mononuclear heme center. Or you can think of non-heme centers, which can be, or non-heme means which having non-porphyrin ligands, and mainly histidines and carboxylate groups. And you can have a dinuclear center having two metal centers, or a mononuclear center. And these are the work actually which I have summarized in the last 30, 40 years on oxygen activation. And there's a consensus basically how O2 activation occurs. Because one of the reasons dioxygen does not react with organic molecules is that it has a triplet ground state. And all the organic molecules, they have singlet ground state. So the reaction of organic molecules with oxygen is a spin forbidden reaction. But nature uses iron or any other transition metals to remove this or to get over this kinetic barrier by converting oxygen, the triplet ground state of oxygen, to a superoxide form. Which is in a doublet state. And then this superoxide, in a series of proton and electron transfer steps, are first reduced to hydroperoxide, and then eventually to the high valent metal oxo species. And this is this metal oxo species which can then perform the oxidation reactions that are targeted. Now, it is generally believed that these high valent species are generally responsible for doing the various oxidation reactions, but there are discussions whether such kind of superoxides or hydroperoxides, they can be also being participating directly in the oxidation chemistry. So one of the things that difference between the mononuclear active site and the dinuclear active sites is that the mononuclear active sites, they need additional protons and electrons to cleave the O bond of dioxygen, but in the dinuclear centers, both the metal centers can provide the electrons necessary for the cleavage of the O bond. Now, there are some enzymes, they also use hydrogen peroxide, which is already an activated form of dioxygen. So you can skip the initial formation of the superoxide. And this is called the shunt mechanism, where you use H2 hydrogen peroxide to directly go to the hydroperoxide species. And then again, the O cleavage to give this high valent species. As I told you, these high valent species then perform a variety of reactions in nature. They can do the halogenation reactions like activating CH bond and forming the CX bond. They can do the hydroxylation, the aromatic hydroxylation reaction, sulfur oxidation reactions, or aliphatic hydroxylation. Especially this is extremely interesting in the context of solving the energy problem, because the natural gas, as we know, has major component methane, and conversion of methane to methanol is one of the main challenges that the industry is facing in a cheap way, and nature does it by using iron and oxygen. So really cheap materials. And also the epoxidation reaction. So it's a very simple chemistry using a transition metal, activating oxygen, generating the high valent metal oxo species, which then performs the oxidation reactions. Now, because of this, and many of this, or rather just to give you an example, a very well-studied example is this enzyme Taurine Dioxygenase, which has again a mononuclear iron site here, and it uses alpha ketoglutarate as a co-substrate. It activates oxygen to form this iron 3 superoxide form, which then undergoes oxidative decarboxylation to generate this high valent iron 4 oxo species termed as intermediate J. And this intermediate J has been extensively characterized in the group of Karsten Krebs and Martin Bollinger by a variety of spectroscopic methods, and it has been shown that it is actually an active intermediate that can perform the CH bond hydroxylation reaction. And in the case of taurine dioxygenase, the substrate is taurine, and this iron 4 oxo then does the hydroxylation of taurine. Now, this inspired many bioinorganic chemists to actually mimic this active site. So Hansen mentioned about Professor Larry Kay, my postdoctoral supervisor, who is actively involved in this research still. The first one who made the model complex, a high valent iron 4 oxo, is my PhD mentor, Professor Carl Wieger. And at that time, this intermediate was, however, or this species was not so stable, but Larry Kay and Professor Wanu Nam, they managed to generate a number of stable iron 4 oxo species, which could be characterized by a variety of spectroscopic methods. And in Germany, if you talk about Peter Komba is also active in this field. There are other people also, this list is not complete, like Miguel Costas from University of Girona, David Goldberg, from US, they are all involved in this interesting field of research. So if I summarize the last 20 to 25 years of research in this field, there have been found out certain differences between this model iron 4 oxo intermediates and that of the intermediate or the biological intermediate. One of the major problem is that in biology, this iron 4 oxo is mainly generated from dioxygen as an oxidant. And for that, at a mononuclear center, you need protons and electrons to cleave the O bond. And not only this iron 4 oxo in biology, they perform CH bond hydroxylation of their own substrates if you feed into these enzymes additional external substrates, for example, a cyclohexene. it has been found out that it performs regioselective epoxidation reaction. So if you take cyclohexene, there are two ways it can be oxidized. Either you do the epoxidation of the alkene, or you can do a CH bond here, an allylic CH bond, which is generally weak, and you can hydroxylate that. So what has been found out in biology that mostly they perform epoxidation and they do not do the the hydroxylation reaction. In contrast, if you take the model iron 4 oxo complexes that have been generated in chemistry outside biology, it has been found out. And the first problem is mostly there are some situations where they have been generated by dioxygen, but mostly they are being generated from stronger oxidants like iodosobenzene. And also they are found to do the regioselective hydroxylation of the allylic CH bonds. In one case, you have preferential epoxidation. In the other case, you have preferential CH bond hydroxylation. So for a long time, it wasn't clear what is the origin of this regioselectivity, or what's the difference in biology and chemistry, that you have very similar intermediates showing very similar spectroscopic properties, but they show different regioselectivities. And one more thing also in terms of, this was dioxygen activation. So also, as I told you, the shunt mechanism, there's some trick about the reactivity of iron 2 and hydrogen peroxide. Now in enzyme, what happens, there's a way how the nature controls this hydrogen peroxide reactivity is that you have the iron 2 center in interaction with the hydrogen peroxide. And there's a histidine brace which performs some kind of a hydrogen bonding interaction, and it controls the transfer of the proton from the proximal oxygen of bound hydrogen peroxide to the distal oxygen of bound hydrogen peroxide. And that leads to the OO bond heterolysis, which leads to the generation of the high valent metal oxo intermediate or iron 4 oxo intermediate. In contrast, in chemistry, in the absence of such histidine base, what has been found out, you get the typical O bond homolysis, which is kind of a Fenton's reaction. So which we all know, like iron and hydrogen peroxide, it does radical chemistry. It's a Fenton's reagent, and you generate hydroxyl radical. And of course, the hydroxyl radicals, if they do, my slides, yeah, okay. So because of the, if it's a radical chemistry, so you should expect uncontrolled radical based reaction. And as soon as you generate a high valent metal oxo species, it performs controlled metal based reaction, which is the regioselectivity. So to use hydrogen peroxide for regioselective oxidation reactions, nature uses this base. That the natural strategy is to use this histidine brace that controls or the proton transfer from the proximal oxygen to the distal oxygen, leading to O bond heterolysis. Generally, in the absence of this base, you have O bond homolysis, which leads to a radical reaction. Okay, so with this introduction, we got interested in this paper. It's a very old paper from 1990s. It was from Joan Valentine, and when Wanu Nam, I talked about, he was a postdoc there, or rather a PhD student, I don't remember. So that was one of his first papers. And they reported an interesting chemistry. They showed that the cyclam ligand, they take a mixture of the cyclam and an iron salt, an iron 2 precursor, and use hydrogen peroxide. It performs regioselective epoxidation reaction. There's no allylic hydroxylation product. So this was kind of an interesting paper at that time, because the first reason is that you use hydrogen peroxide for regioselective reaction. So that means you somehow avoid the Fenton's mechanism or the radical based mechanism. Secondly, at that time, they proposed that the actual species, the active species performing this reaction is iron 3 hydroperoxide species. Why? Because iron 4 oxos that have been generated or stabilized, they all performed typical hydroxylation reaction, not much of epoxidation reaction. So that's why it was believed that time the actual species must be an iron, or the intermediate that performs this epoxidation chemistry must be an iron 3 hydroperoxide species. but the spectroscopic evidence was missing and it wasn't clear what is the active species. So we got interested in determining the mechanism of this reaction. So why, first of all, hydrogen peroxide performs a regioselective epoxidation, and the second, what is the active species which is doing the reaction? So that time, so what they did, they took the cyclam and took the iron precursor like an iron perchlorate salt, and they generated the iron cyclam complex in situ. They didn't characterize. So we got involved, we got interested, and we thought, okay, let's characterize the different species that forms in the reaction of iron and cyclam. So we took the cyclam, we reacted that with iron, and we were quite surprised that there are actually two isomers that are forming. One is the cis isomer, where the two binding sites are cis to each other, or the two labile sites where the substrate can bind. And there's the trans isomer where they are trans to each other, the two acetonitrals or the two labile sites. And we had a crystal structure, and the crystal structure showed two vital things. Not only they differ in terms of their cis and trans orientation, they differ how the hydrogens are oriented. In case of the cis isomers, the two opposite hydrogens of the cyclam ring, so that would be these two, they are cis to each other and cis to the cis binding sites. And in the case of the trans, the two adjacent ones are cis to each other, and the two others are trans. So it's kind of two up, two down, and here it's also two up, two down, but here the up, the ones that point towards the cis binding sites are the opposite nitrogen atoms or the NH groups. We were also quite surprised to find that only the cis isomer actually acts as the active catalyst. And the cis isomer is also the kinetically controlled product because it's formed first. So as soon as you add cyclam and iron, you form the cis. And then if you keep stirring the solution, it changes to the thermodynamically controlled product, which is the trans isomer. And if you put light into the trans isomer, it moves back to the cis. So these are interconvertible in solution. And as I told you, only one of the isomer is actually catalytically active, that is the cis isomer. And when we took this cis isomer and we tried the catalysis, and we indeed found that if we put cyclohexene or other alkenes, it gave preferential epoxidation product, and no allelic oxidation product was observed. So they perform really regioselective epoxidation reaction. So what is the origin of this regioselective epoxidation? So, and also what is the reactive intermediate which is doing the chemistry? So we do stock flow studies in our lab. So where we mix the substrate and the oxidant, or the catalyst and the oxidant in a syringe, and then we transfer them in a specified time and freeze them immediately by the rapid freeze quench investigation. So we trap reactive intermediates during the course of catalysis and characterize them by various spectroscopic measurements. So you can do this in the times range of 5 to 4,000 milliseconds. So what we found out first, that under catalytic turnover conditions, we saw when we did the UVV studies, we saw a band developing around 750 nanometer. And as you can see the time trace, and it develops within 2 seconds and then undergoes a fast decay. So we could see an intermediate in the first 2 seconds, and then there was a fast decay of that intermediate. Of course, within 2 seconds, you can't do much. So we thought, okay, so what happens if this intermediate can also be generated in the absence of the substrate? And indeed, we found out that it became stable around minus 40 degrees Celsius in the absence of the substrate. And then you see that it's quite, the absorbance doesn't change much as a function of time. So it has a stability of over 400 seconds. Now, 400 seconds is not enough time to crystallize this intermediate and to see how it looks like, but we had all the time in the world to actually determine what it can be. So there are lots of spectroscopic measurements that can be performed within this 400-second regime that can give you an idea about the nature of this intermediate. So what we did, first we wanted to get structural information about this intermediate, and we use extended X-ray absorption, a Fourier transform spectroscopy. So what is, so what we do here in XF spectroscopy is that you use X-ray to take a core electron from the metal, which then flows as a wave, and then it hits the metal and it creates a secondary wave. And from the interference between the primary and the secondary wave, you get an idea about the metal ligand distances. And this is what we did, and this is the XF spectrum. And by the simulation, what we found out that the iron has actually 6 coordination ligands in its immediate environment, and 5 of them at a distance of 2.01 angstrom, and 1 short distance of 1.66. And this short distance we assign it to an iron oxygen bond. And indeed, when we did that, perform the DFT calculation, so we could the DFT and the XFs determined distances were in quite a good match to each other. So the XFs provided an evidence we may actually forming the intermediate that we trapped is actually the an high valent iron oxo intermediate. So 5 nitrogen donors, 1 oxygen donors, and in good agreement with the DFT studies. So we then wanted to do some NMR studies to find out if we really have, we start from the cis isomer. Do we also get this cis isomer of the oxo complex where the astronitrile and the oxygen are in cis orientation to each other? And indeed, so for that purpose, we synthesized the deuterium labeled cyclam core. And this study was done with Jason. We actually sent some of our samples to Singapore. And he was kind enough to do some of the measurements there. And what basically we found out that for the cis isomer, you should expect 13 signals. And for the trans isomer, for the deuterated ligand, you should expect 7 signals. And of course, we could assign the 13 signals here. And that was in good agreement, the NMR, with that we do have a cis isomer and not the trans isomer. The major problem was that eventually we have crystallized the trans isomer. We'll come to that. At that time, when we did the NMR studies, we didn't know if it was possible to actually synthesize the trans isomer. So the NMR studies was very helpful at that time to get an idea about this intermediate. Okay, so then we wanted to, or maybe I'm making a mistake. Jason, maybe you didn't do this, the measurement of this. You come later with the next paper, right? Sorry, I think I confused myself here. So this NMR was done in Germany. Jason studies, I think he performed another intermediate, which I will also come. Yeah, sorry about that mistake here. Okay, good. So basically this is a paramagnetic NMR. It showed us that the spin state of this compound, the compound is actually paramagnetic. You can see the hydrogens are split in a wide range. And it showed the 13 signals expected for the cis isomer. We also did further studies. We did the X-ray absorption near edge spectroscopy, and we saw that the dashed line corresponds to the starting iron 2, and the bold line corresponds to the iron 4. Or rather the intermediate that we trapped, the edge shifted by 2 electron volt, and the pre-edge becomes much stronger, which are typical for high valent metal oxo species. The pre-edge becomes much stronger because you increase the covalency by mixing of the oxygen p orbitals with that of the iron d orbitals. So everything was consistent with an iron in +4 oxidation state. And most power studies confirmed it has actually a spin triplet ground state, because you will see later that iron 4, it has 4 d electrons, iron in +4 oxidation state. And there are 2 possible spin states. Either you can have 2 unpaired electrons, s equal to 1, or you can have 4 unpaired electrons, s equal to 2. But based on the most power studies, we confirmed that it has actually a spin triplet ground state. Okay, good. So just to summarize whatever we have learned so far, so we have this cis and the trans isomer, and what has been found out that both in the cis and the trans isomers, they have actually an S equal to 0 ground state. And in one of them only reacts with hydrogen peroxide to generate this iron 4 oxo species. This is the catalytically active species which can perform regioselective epoxidation reaction. The trans isomer, we found out that it is kind of very stable and it does not react with hydrogen peroxide to generate this high valent metal oxo species. So two questions. So why only the cis isomers react with H2O2? And somehow it avoids the radical pathway. The trans isomer cannot form the metal oxo species, and the reaction with H2O2 it leads to the typical Fenton's reaction. So coming back to this nature, how nature does the hydrogen peroxide activation, it uses a kind of a histidine as a base which controls this movement of the proton from the proximal oxygen to the distal oxygen, and that leads to the O bond heterolysis, and this is very important if you want to avoid the radical chemistry. So we got interested what is performing this, what makes us avoid this radical based chemistry, and we found out from the DFT studies that these two hydrogens, which are actually in cis orientation with the two binding sites or the labile sites where the substrates or the oxidants can bind. It's very important for this chemistry. So there are two hydrogen bonding interactions which helps in the binding and the cleavage of the hydrogen peroxide. So here, first of all, this NH group performs a hydrogen bonding interaction here, and that helps in the binding of the H2O2. And once it's bound, the second hydrogen bonding interaction actually helps in the cleavage of the O bond, leading to the heterolysis. As you can see, this step is extremely energetically favorable because of this H bonding interaction, which makes the this O bond heterolysis step extremely favorable. So these NH groups actually acting as the histidine base, which nature uses to cleave the O bond heterolytically. So hydrogen bonding interactions, it's actually very important in catalysis. And this is what we found out, that this is a very important step for generation of this high valent metal oxo species. Now we generated this high valent metal oxo species, and we found out indeed, even in stoichiometric reactions, if you take these substrates, they actually lead to regioselective epoxidation. The allylic products are very minor, yeah. So they all lead to preferentially epoxidation reactions. So the question is why? What leads again to this? What makes this intermediate avoid the allylic CH bond hydroxylation reaction, which have been previously observed for most of the iron oxo complexes or iron oxo intermediates? So what we found out that here again, or what we presently believe, that the NH groups, the hydrogen bonding interaction again helps in the regioselectivity. So what we think, you may tell me a bit crazy in this, but we have some indirect evidences. We think the alkenes actually undergo hydrogen bonding interaction with these NH groups. And that brings the alkene close to the metal oxo, so that there's no way it can perform the CH bond abstraction, rather it transfers the oxygen. And in favor of this, what we found out, that if we replace these NH groups with deuterium, we actually see a kinetic isotope effect in a preferentially or a predominantly oxygen transfer reaction. So we see a kinetic isotope effect of 1.4. So there's no transfer of protons involved in this epoxidation chemistry, and nevertheless, if we replace the NH with deuterium, we see a KIE. And based on that, we think that this kind of hydrogen bonding interactions are operating in this case which leads to the regioselectivity in the epoxidation chemistry. Okay, and this kind of alkene hydrogen bonding interaction with alkenes and NH or OH groups are not that unknown. I mean, there are certain cases. Of course, these are OH groups. The NH groups I don't know of, where the alkene performs these hydrogen bonding interactions. There's this paper in Journal of Organic Chemistry. They have the crystal structure of this intermediate. And also in Chemical Science in 2015, where they showed an OH group performing hydrogen bonding with the alkene. Whether an NH group can do that, we are trying to find it out. Some more research activities are going on in that respect. So it is really the hydrogen bonding interaction which helps, first of all, to generate the metal oxo species in presence of hydrogen peroxide. And next, it helps us, it helps the metal oxo to perform regioselective epoxidation reaction. Okay, good. So here again, this is the summary. So the cyclam iron 2 isomers, one of them reacts with hydrogen peroxide to generate this metal oxo, regioselective epoxidation because of hydrogen bonding interaction. The trans, it doesn't show the metal oxo reactivity or the formation, or doesn't perform the metal oxo formation in presence of hydrogen peroxide. But it would be good we tried with various other ways, and there are other ways to generate metal oxo species. So we wanted to actually synthesize this trans isomer and to compare the different reactivities. With hydrogen peroxide as an oxidant, it wasn't possible, but we could find out that with iodosobenzene, we can actually generate this metal oxo species. So this cross, I don't know, it has somehow come. So it means that first of all, we could get access to this trans isomer. Not only that, we found out, in contrast to the cis isomer, which is extremely reactive and it can be only stabilized at low temperature, this species, the trans isomer, is actually highly stable. It's unreactive, and to an extent that we can actually crystallize this species. So we obtain crystal structure of the trans isomer. So all we had to do is to use a stronger oxidant like iodosobenzene. Of course, the hydrogen peroxide way didn't work out. And this gave us an option, because we have now two different metal oxo species with contrasting reactivities, to understand what's the origin of the differences in the reactivity in the two cases. So we initially thought, has it something to do with the metal oxo distances or the iron oxygen distances? Because it may be that in case of the cis isomer, the iron oxygen is much more activated. But what we found out, the distances that we obtained from XAPs for the cis isomer and for the trans isomer from the XRD, or the extra diffraction from the crystal structure, they are very comparable. So 1.66, 1.67. Even the cis isomer has a slightly shorter metal oxygen distance. So it has nothing to do with the activation of the iron oxygen. So do they have different spin states? We thought, can they actually have different spin states? And one way to know that, you do magnetic Morse power studies. So you do Morse power in varying fields, and that was done in cooperation with Eckhart Bill. And what we found out that these are very clear cases of spin triplet ground state. So that means it's iron in +4 oxidation state, you generate the iron 4 oxo, and we got a very nice fit for S = 1. And the spin Hamiltonian parameters are very comparable to each other, which showed that both of them in their ground state, they are spin triplet. So that means D4 system, an octahedral geometry, you have the we have the two unpaired electrons in the DXC and the DYZ orbitals. But however, we saw some differences in the absorption spectrum. So the black represents the absorption spectrum of the starting iron 2, the cis isomer. And when we generated the iron 4 oxo, it showed a typical band at 737, which Ed Solomon and others, they have shown this band originates from the ligand field excited states of an iron 4 center. And what we found out that this band is much more, is redshifted in the cis isomer as compared to that in the trans isomer. So it's 737 nanometer versus 582 and 690 nanometers for the trans. Now, as I told you, this band actually from MCD studies has been found to correspond to a dxy to dx square minus transition of the S equal to 1 ground state. So that means it corresponds to an electron transfer or excitation from the dxy level to the x square minus y square level. And dxy dx square minus y square energy gap actually represents how far the excited state, the high spin state, is from the ground state. So basically, this is a measure of the energy gap between the ground state and the excited state. And the fact that this is much more redshifted in the cis isomer told us that in the cis isomer, actually, the excited state is much more lower in energy. So in case of the cis isomer, the S equal to 2 state is lower in energy. And that's the reason what we presently think why the cis isomer is so reactive, because of the two states, although the ground state is spin triplet, there's a big discussion in the bioinorganic community that iron 4 actually, or iron 4 oxo, it performs reaction at excited S equal to 2 state. That's why S equal to 2 is actually the preferred state that nature uses for doing various oxidation reactions. So the question is now why the S equal to 2 state is more reactive. This comes from this theory that Sashan Shaikan has put forward. So if you want to use an iron 4 oxo species for carbon hydrogen bond activation reaction, so you need to transfer a proton and electron to the iron 4 oxo core. So the iron 4 oxo core in the S equal to 2 state, the dz square orbital is actually lower in energy because of 4 unpaired electrons, and it has an exchange enhanced reactivity also. And what happens, the CH bond can actually transfer its proton and particular electrons to the dz square orbital. And the z axis is along the iron oxo, so that means it prefers in the S equal to 2 state a linear approach of the substrate. In contrast, what happens in the S equal to 1 state, the dz square orbital is quite high up in energy, so the actual electrons from the CH, they go to the dyz and the dxz orbitals. And that would mean you need a pi approach of the substrate. The substrate should come perpendicular to the iron oxygen axis. And you can imagine now with all these equatorial ligands, there's a lot of steric interaction of these substrates. And correspondingly, the S equal to 2 state has a much lower activation barrier for CH bond or hydrogen atom abstraction reactions or CH bond oxidation chemistry in contrast to the spin triplet state. So even if all these intermediates have a spin triplet ground state, it has been proposed a 2-state reactivity where they either need to transfer to the excited state before they do the hydrogen atom transfer reaction, or they need to tunnel into the excited transition state during the hydrogen atom transfer process. So that means the reactivity of an iron 4 oxo core will be determined by the energy gap between this ground S equal to 1 state and the excited S equal to 2 state. Lower is the energy gap, higher is the reactivity. And in case of the trans isomer, the lower energy gap is represented by the red shift of this characteristic iron 4 band, which is consistent with its higher reactivity. So this is a good example why spectroscopy is so important, because you can exactly correlate the spectroscopic characterization to the reactivity of this species. Good, so basically we could understand why this cis isomer is so reactive, because it has weaker equatorial field, which brings the x square minus y square level lower in energy, and correspondingly the excited state is lower in energy. Good. Now coming back the mechanism of the generation of this trans isomer. So the corresponding trans isomer is known for some time. So we had been using the cyclam ligand, but Larry K and others, they used the methylated version, because initially it was thought that if you have an NH group, they should be, they can be easily oxidized by an high valent iron 4 center. So people didn't use the NH group cyclam in the high valent metal. They tried to avoid those chemicals, but we decided to use it, and we found some interesting stabilizing effects of these NH groups in the iron 4 oxo chemistry. And here is another example. So if you, so the initial science paper from Larry K and Wanunam, and there was a recent Nature paper, they actually summarized this iron 4 oxo chemistry based on this methylated cyclam ligand. So they started with this iron 2, and they found out they can generate the iron 4 oxo either with iodosobenzene, or they can use oxygen in presence of protons and electrons. Of course, to cleave the O bond, you need additional protons or electrons, and it's a mononuclear metal center. And there have been other ways you can generate that. You can also do the shunt mechanism, hydrogen peroxide. You form the peroxo, which in presence of proton forms the hydroperoxo and gives the iron 4 oxo. So all these cycles, the way in nature O2 activation occurs, it could be shown with this iron cyclam chemistry. So that really helped this chemistry to establish how the dioxygen activation chemistry occurs in biology. Now, one thing now what we found out, that if we now replace these methyl groups with hydrogen, we do not need anymore this proton and electron to cleave the O bond. So if we now move from the methylated version to the NH group, we found out we just use O2 or iodosobenzene and we get this trans isomer. So we were quite surprised. So we were thinking, if you want to cleave the O bond, this is a mononuclear center, what is the source of proton and electron? And then we tried to find out if this oxygen, if we do the reaction with oxygen, if the oxygen of the oxo really derives from the dioxygen, it is indeed the case. So the blue one is the iron 4 oxo, the resonance Raman data. We saw a band at 840, 2 wave number, which is the iron oxygen stretch. And when we generated the iron 4 oxo with O18 oxygen, we saw it's getting split into 2 at 800 and 813. So if we take the average by taking this as a Fermi resonance, so the shift is around 36 wave number, which is kind of the shift that you expect when you replace the O16 with O18 for an iron oxo vibration. In the mass also, we saw a shift of 2 units when we replaced O16 with O18. So it clearly showed that the oxygen derives from the dioxygen. The Moss power was clean, so it's a very clean reaction. And it showed we have an iron 4, and the EPR, was EPR silent except a very broad band. So all these things, it showed that it's a very clean reaction, starting with iron 2 oxygen to iron 4 oxo. So then basically if we go back to the natural way of activating dioxygen, you react with iron O2, you form the superoxide at a mononuclear center, and then protons and electrons, and it converts to the iron 4 oxo. But we do not have any proton or electron sources in we just put O2. And we initially thought maybe the solvent, the acetone that we are using, that's delivering the proton and electron. That's also not the case, because we deuterated the acetone and we didn't see any difference in the rate of the reaction. So the only thing that comes out is the dinuclear mechanism now, that you have, instead of 2 iron centers, or rather 1 iron center, if you do not want to use protons and electrons, the second iron must be providing the electrons necessary for the cleavage of the O bond. And indeed, if this is found out, and this is the mechanism which is believed to be occurring in soluble methane monooxygenase that generates the high valent metal oxo species, which then performs the oxidation of methane to methanol. So we did some detailed kinetic studies with the trans isomer, and what we found out, so the black is the starting iron 2. Upon reaction with dioxygen, it forms an intermediate, which is shown in this green. And then this intermediate decays to the iron 4 oxo species. And another interesting aspect of this reaction that we found out, that more oxygen you give, first of all, it's a second order with respect to iron. And also we found out that more oxygen you give, the reaction becomes slower. So higher oxygen and slower. So this is the red is the reaction rate in air, and the blue is the reaction rate in pure oxygen. Of course, in air, the concentration of oxygen is much lower, and we also use different ratios of nitrogen and oxygen. And we found out that with increasing oxygen concentration, the rate decreases. So this was kind of surprising that if you increase the oxygen, then the rate decreases. And in the conversion, we also found out that the intermediate is converted to the iron 4 oxo in such having such isospecific point. So it's a very clean conversion. So we trapped the intermediate and we characterized it by a variety of spectroscopic methods. So Zen studies showed that it has age and pre-age data in between the starting iron 2 and the iron 4, and it's confirmed by Moss power that it has actually a low spin iron 3 species. And from resonance Raman, we could identify a band at 1147, and upon O18 shifting, it vanished, and we think that it shifted under the solvent band. So all these kind of provide evidence that we actually form an iron 2 and oxygen first and iron 3 superoxide species. And then this iron 3 superoxide, in the absence of additional protons and electrons, get transferred to the iron 4 oxo species, which is kind of very unique, because where are the additional electrons coming from? And we found out later that this superoxide species has some unique characteristics. It's a very strong oxygen transfer agent, even stronger than iron 4 oxo. And if you give any triphenyl phosphine to that, it transfers one of its oxygen to the triphenyl phosphine, oxidizing it to phosphine oxide and generating the iron 4 oxo. So the iron 4 oxo does not react with triphenyl phosphine, but the superoxide does. So it's a very unique case where the superoxide is more reactive actually than the high valent intermediate. And this transfer you can see here. So upon reaction with oxygen, you see the development of the band at 360, and the red and the green corresponds to the iron 4 oxo. So there are slight forming, but the moment you put now triphenyl phosphine, the superoxide decays and you generate the iron 4 oxo. Yeah, so it's a very clean reaction. And what's happening here, and this is the rate constant as a function of O2, and you can see with increasing O2 concentration, the rate constant decreases linearly. So what's our mechanism that we propose is that the iron 2 and oxygen forms this iron 3 superoxide in a pre-equilibrium state, and the equilibrium lies at the side of the superoxide. And then this superoxide is a very strong oxidant, and it reacts with this, as soon as it is formed, it reacts with the second molecule of iron 2 to generate 2 molecules of iron 4 oxo. And the iron 2 can also be replaced by a substrate like triphenyl phosphine, which actually performs the oxygen, the function of an oxygen atom acceptor, and it also generates iron 4 oxo. So it's a unique mechanism. So what is the reason for this high reactivity of this superoxide? Here again, we think that the superoxide, in case of this NH ligand, is stabilized by this hydrogen bonding interaction. So this is the DFT calculated structure, but the superoxide has a strong hydrogen bonding interaction with the NH group. Of course, if you replace the NH group with a methyl group, the hydrogen bonding interaction vanishes and you do not form the superoxide anymore, and it performs a completely different mechanism for O2 activation. So this is one of a very unique case where hydrogen bonding interaction actually controls the mechanism of O2 activation. So if we have in one case the methylated cyclam versus the non-methylated cyclam, in this case you have a hydrogen bonding interaction. The red represents the non-methylated cyclam. So the hydrogen bonding interaction stabilizes the iron 3 superoxide. Not only that, this hydrogen bonding interaction makes it makes this iron 3 extremely electrophilic, and it makes this a stronger oxidant, even stronger than the oxo, and that results in it to transfer its oxygen group to iron 2, generating this iron 4 oxo species. If you replace this hydrogen with the methyl group, then you have the typical mononuclear mechanism where you need additional protons and electrons to go to this iron 4. So this is kind of a very similar ligand platform, but with initiation of hydrogen bonding interactions, you change the mechanism of the dioxygen activation. This is in addition to the hydrogen peroxide chemistry, where we also showed that hydrogen bonding interactions are very important. So as bioinorganic chemists, many times we try to mimic the active site of the enzyme, and many times we forget about the secondary interactions that the protein backbone can perform. So this is showing that these kind of secondary interactions are actually very important in providing mechanistic alteration or differences in mechanisms by which small molecule activations can occur. Okay, how am I doing with the time?
So, I mean, it's okay. So you have about 10 minutes left, but we also want to reserve some time for question and answer.
So maybe then I stop here because I still have, so maybe, okay, I take another 2 to 3 minutes.
Sure, no problem.
Okay.
Yeah.
And so this was about the hydrogen bonding interaction. So, and in the importance, the next thing we also was interested in about mimicking the active site of this interesting intermediates, because these are the various iron 4 oxo intermediates that have been stabilized or trapped in biology, and you can see that many of them, they actually have oxygen or carboxylate, weak carboxylate ligands in addition to histidines. And if you consider the various model complexes that I told you have been synthesized, they're mainly based on strong field ligands like nitrogen or carbines. So we got interested because cyclam is something is very easy to modulate. Can we actually investigate why nature uses oxygen donors rather than strong field donors? And one of the things that we found out that if you compare the reactivity of the enzyme with that of the different model complexes, this is, for example, the cyclohexane oxidation reactions, and this is the second order rate constant. The enzyme is here, 15,000 into 10 to the power minus 4, and the model complexes are way, way behind. So 3 to 4 orders of magnitude slower than that of the actual enzyme. So we thought, and this may be actually corresponding to the, because of the strong field ligands, nitrogen donors that are being used in most of the cases, in contrast to biology, which uses this histidia, these carboxylates. And that would also, the weak field donors that are being used in biology would also stabilize the more reactive S equal to 2 state, and most of the intermediates that are known, they have an S equal to 1 state. I guess Jason made the first S equal to 2 compound, but they are the sterics with the TMG3 trend ligand, but the sterics necessary to stabilize that also reduce the reactivity to some extent. So these are some of the reactive intermediates, and they have still way, way behind in terms of the rate. So we started this project where we thought, can we introduce oxygen donors into this cyclam backbone? And our initial idea was to make this ligand, and we actually made this ligand. We made the complex where you can see the oxygen actually binds, and that really reduces the equatorial donation. And we had a very clean Moss power. And eventually we made the iron 4 oxo, not again with oxygen, but with such iodosobenzene. And we characterized that by various spectroscopic methods. We still found it to have a spin triplet ground state. But one thing we found out, in contrast to the cyclam, which was way behind, which did not react with cyclohexane, now just by replacing one of the nitrogen with oxygen, we increased the reactivity significantly, and now we are just 1/2 the rate of the enzyme. So basically, oxygen donation, introduction of one oxygen, significantly increases the rate of the reaction. And this we found is not because of sterics. So basically the sterics is almost the same in the two cases. This is the TMCO or the oxygen substituted one, and this is the cyclam. And here we found out again, with weakening of the equatorial donation, you actually bring the excited S equal to 2 state very close in energy, so that in case of this with oxygen substitution, the high spin and the intermediate spin, the S equal to 2, and they're almost degenerate in energy. In contrast, they're well separated in the cyclone case. So the more reactive S equal to 2 state is actually performing the reaction, and it's much lower, more available. And that's why it performs this very fast hydrogen atom abstraction from the substrate. So this is like where you can tune the electronics around the iron center, the equatorial donation to increase the reactivity. Okay, so I guess in the interest of time, I skipped the dioxygen reduction part, where we had a catalyst. So we used, so far whatever I discussed is about the oxygenase activity, where you activate oxygen to generate high valent metal oxo, and then the oxo species is then transferred to the substrate. You can also think of activating oxygen and reducing it completely to water. It's a very important reaction in the context of fuel cell. And we found in 2017, we found a very important catalyst where we found out that it actually performs, you can control the selectivity. So oxygen you can reduce by 2 electrons to hydrogen peroxide, or by 4 electrons to water. And it found out a very interesting catalyst where by changing the temperature, you could change the selectivity. We found out at minus 50 degrees, you form a peroxide, which then performs a proton coupled electron transfer to generate water. So it performs 4 electron reduction process. In contrast, the peroxide is unstable at higher temperature, at room temperature, and then it performs a 2 electron process and releases hydrogen peroxide. So the same catalyst, just the summarized slide, the same catalyst, it performs at high temperature 2 electron reduction of dioxygen to hydrogen peroxide, and at low temperature 4 electron reduction of oxygen to water. And we did a lot of spectroscopy to understand what controls this proton selectivity or deselectivity for the dioxygen reduction. Okay, to summarize, so what we are trying to do, we try to understand dioxygen cleavage to water. We also try to understand water oxidation to dioxygen. So these are very important reactions. In nature, they are both mediated by transition metals. In one case, you do O bond formation, and in the other case, you do O bond cleavage. And you go and form very similar intermediates like metal superoxide, metal peroxo, metal hydroperoxide. And the equilibrium between these two actually determines which way you will do, whether you do O bond cleavage or you do O bond formation. And there are many studies that have been done in recent years, and what we are trying to find out how you can tune the electronics and the sterics to some extent to see this equilibrium. But there are nevertheless, there are many questions, there are open questions in this field, like how exactly the O bond formation occurs. Also, nature uses in the photosystem too, nature uses calcium to initiate the O bond formation, what its actual role. We also try to understand there are different enzymes which uses very similar active sites to perform very different functions. In one case, electrophilic reactivity, in some other case, nucleophilic reactivity. So we try to understand, once the metal oxygen intermediates are formed, how can you control the electrophilicity versus nucleophilicities? In particular, we try to understand what are the different factors that control the reactivity of the metal oxygen intermediates. And today we could show how hydrogen bonding interactions are very important in generating high valent metal oxos and controlling their reactivity. So if you are interested, we have written many reviews in collaboration with different people who are actively involved in this field. So you are welcome to read these reviews if you are interested more into this field, how biomimetic chemistry can provide vital insights into how dioxygen or other small molecules are activated in nature. Okay, so this project that I talked about today on dioxygen, these were done by these 3 excellent ladies who unfortunately they have left my group and they have started all their own career, and it has been taken over by Dustin Kass, an excellent student also. He just started his PhD, and the work that that I showed you about the cyclone, that was a part of his master's work, and luckily he decided to stay to perform his PhD in my group. I had some excellent collaborators, Professor Wanu Nam, we are actively involved in that. Eckhard Bill performs most of the magnetic mass power fields or the studies. So we have at Humboldt University mass power, we can measure that, but to determine the spin state, we need to send our samples to Eckhard. Marcel Swart performs the DFT calculations, many of them. Cassie, actually, I didn't have chance to speak about the Cobalt project on the dioxygen reduction, which we wanted to talk about. He did the DFT calculations and many spectroscopic characterization. Jason Mesher did some of the NMR studies for our oxygen substituted cyclam ligand. Resonance Raman studies, I thank Professor Peter Hildebrand from TU Technical University Berlin for providing access to his instrument. We do excerpts on our own, but because of the UNICISCAT collaboration, we do also cooperations with Holger Dau, Michael Haumann, and also with Eric Farquhar, a very good friend of mine, who we send samples to him sometimes, and he does the measurements and the analysis. It's very helpful. And Nikolai Leonard, we cooperate. We have a long-time collaboration on the MCD studies and various spectroscopic investigation of the reactive intermediates. Money is important. I'm really thankful to the Heisenberg program that allowed me to stay in Germany. This Heisenberg professorship and the UNICISCAT, the cluster of excellence, and the cost, which helped me to get to start many important collaborations within Europe. Thank you very much for the invitation again. I really enjoyed giving this talk, and I'm looking forward to your questions then and the discussion. Thank you very much.
Thank you, Kallol, for the very recent update of your latest work. It's very interesting. I must say that I actually did not manage to catch up with so much new results from your group. So now the floor is open for questions. You can either give a thumbs up before asking a question, or you can just go ahead